Here's a data set. 3 values are reported as greater than 6.5, but you don't know their exact values. So here's the question. What is the average? If I fill those in as 7.5, 7.0, and 7.2, the mean is 5.64. But if I instead use 6.6, 6.6, and 6.5, the mean drops to 5.14. Same data, 2 different answers. So which one is correct? The uncomfortable answer is, you can't tell from the data. Those values are not observed. They're only known to be above a threshold. I'm Jose B., the traveling medical data scientist. I work with clinical and survival data where this issue comes up all the time. So what went wrong here? And what should you use instead? What we just saw is not a one-off example. This same issue appears frequently in clinical data, particularly in laboratory testing, where instruments sometimes report values as outside their measurable range instead of giving an exact number.
So here's the problem. How can we estimate the center when some values exceed the detection limit?
Let me give you some background so you can see how often this comes up. For people living with HIV, viral load is a key measure of disease status. But PCR-based assays have a lower limit of detection, so very low values are not measured exactly. Results below this limit are reported as less than 20 copies per milliliter, or undetectable, meaning the exact value is unknown but lies below the detection threshold. People who maintain an undetectable viral load on treatment do not transmit HIV through sexual contact. This is known as U equals U, meaning undetectable equals untransmittable. The problem is that undetectable is a categorical label, not a numerical value. We do not know the exact viral load for a person with an undetectable result, so if we want to treat it as a numeric variable, how should we represent it in the data? In public health, the Centers for Disease Control and Prevention, or CDC, reports family size as 1, 2, 3, and so on, but at 8 it often switches to 8 plus, meaning 8 or more people. For families with 8 or more members, the exact family size is unknown. In engineering, machines may report greater than 10,000 newtons if a metal rod does not break. Again, the exact breaking force is not known. In each of these examples, the exact value is unknown, but is known to lie above or below a threshold. Now let's return to the problem from the beginning of the video. Clinical chemistry analyzers measure potassium in blood. Normal range, 3.5 to 5.0 millimoles per liter. A lab scientist receives a report of serum potassium levels for a group of 9 patients. She notices that 3 of the 9 patients have abnormally high readings, but their exact potassium levels are unknown because they exceed the measurement limit. How should she compute the average? The scientist does not know the true values of these samples reported as greater than 6.5 millimoles per liter. The challenge is that the true values of these 3 observations are not known. The main problem is how to summarize the center of the data in a way that reflects what most values look like. A long list of numbers is hard to understand. A short summary can show patterns and typical values. To do this, we often use a measure of center, such as the mean or the median. However, the mean is hard to calculate because some values are not fully observed. We can attempt to complete the data by making assumptions about what the unobserved values might be. At the beginning of the video, we saw these 2 possible data sets. They were created by filling in values that exceed the measurement limit. The key point is that the mean changes depending on what we assume about values above 6.5. However, if we calculate the median, we find that both data sets have the same value. This shows that when the highest values are not fully observed, the median is less sensitive to extreme values and does not rely on assumptions about censored values, which makes it a more stable measure of center. The examples we've looked at are examples of data with censored values. A value is censored when it is not fully observed. Viral loads less than 20 copies per milliliter are one example. Serum potassium levels greater than 6.5 millimoles per liter are another. In each case, we only know that the value is above or below a certain limit. In other words, the data are not missing, but they are incomplete. Values in a data set can be either observed or censored. These are the observed values because they are fully known and measured exactly. These are the censored observations. In particular, they are right-censored, meaning they are greater than 6.5 millimoles per liter, but their exact values are unknown. On the other hand, these are left censored, because the true viral load is unknown, but below a detection limit, here 20 copies per milliliter. Censored data often arise in studies where the outcome is time to death. I have taught survival analysis to biostatistics and applied epidemiology students for many years, and have published peer-reviewed work in collaboration with cardiothoracic surgeons. In several of these studies, the outcome is survival time, measured as the number of days from surgery to death. At the time of analysis, many patients are still alive, so their survival times are censored. For example, a recorded survival time of 179 days may simply reflect that the patient is still alive, so the true time to death exceeds 179 days. This is censoring. The observation exists, but its exact value is unknown, and we only know it exceeds a given time point. It is not missing, only incomplete. To decide which average to report when data are censored, we consider the following. The mean needs exact values, but censored values are not known, so we have to guess them. Different guesses give different means. For this reason, the median is often preferred when data are censored. When choosing between the mean and the median, the key issue is this. With censored data, the mean requires assumptions. To compute it, you must assign values to the censored observations. These values are not observed, so they cannot be verified from the data alone. As a result, different assumptions can lead to substantially different means. Software like SAS recognizes this problem when estimating the mean survival time when data are censored. In the output, it provides the warning. Note: the mean survival time and its standard error are underestimated because the largest observation is censored. In plain English, SAS is basically saying, this isn't the true mean, it's an underestimate because some of the longest survival times are incomplete. But SAS doesn't stop you from reporting the mean, and it doesn't force you to use the median either. It just gives you the warning and assumes you'll use some judgment when interpreting the result. So we said that using the mean with censored data requires assumptions about the censored values. Does the median avoid this problem? Not in all cases. If the median can be found using only the observed data, then it does not depend on any assumptions. This happens when at least half of the observations are fully observed, and the middle value falls among them. In this case, the censored values only affect the extremes. The middle is already known, so changing assumptions about the censored values does not change the median. The median becomes uncertain when the middle of the data falls within the censored region. This occurs when many large values are right censored or many small values are left censored. In this example, we have 10 observations, 6 of which are censored. As a result, the median cannot be determined exactly without making assumptions. Different assumptions about the censored values can therefore lead to different medians. Let us examine this example more closely to illustrate the limitation of the median. In both datasets, we start with the same observed values, 3.7, 4.0, 4.3, and 4.8, along with 5 values known only to be greater than 6.5, so the median is the 5th ordered value out of 9 observations. In the first dataset, we replace the censored values with numbers just above 6.5, making the 5th value 6.6. In the second dataset, we replace them with larger but still plausible values, making the 5th value 8.2. Even though the original data are identical, the medians differ substantially. This shows that when the median itself falls in the censored region, it depends on how the unknown values are filled in, so different assumptions can lead to very different medians. How does this apply to survival times? As we saw in the previous slides, the median cannot be determined when the middle of the data falls in the censored region. The median survival time is an important statistic, both as a summary measure and for comparing groups. Now consider the extreme case. Suppose no patient dies during the study. In this situation, all survival times are right censored. We only know that each patient has survived at least up to their last follow-up time, but we do not know the exact time to death. Because of that, there is no information about the 50th percentile, so the median survival time cannot be determined. More generally, if fewer than half of the patients have experienced the event, the median lies in the censored region and is not identifiable from the observed data. So here's the key takeaway. In this video, we focus on measures of center. When a lab instrument reaches its limit of detection, the data becomes censored. The exact values of some observations are unknown. We only know they lie beyond a threshold. Any summary that relies on those unknown values will depend on assumptions. Measures of variability raise additional issues and will be discussed separately. The mean requires complete data. With censored data, it no longer comes from the data alone. It depends on assumptions. The median requires that the middle of the data lies in the observed region. It only depends on assumptions when the 50th percentile is censored.
You've seen the explanation. Take the quiz to check your understanding. Then, try the challenge problem if you want to go deeper.
Here's today's quiz. A lab measures a biomarker, and the machine cannot detect values below 2 units. Suppose you collect the following 7 observations. Less than 2, less than 2, 2.5, 3.0, 3.5, 4.0, 4.5. What is the mean? What is the median? The mean requires that all 7 values are known. Can the median always be determined when data are censored? Feel free to pause the video here and take a moment to work through the quiz. To find the median, we order the data, which has already been done. The median is the middle value, the 4th out of 7 observations, which is 3.0. Unlike the median does not require all values to be known. It only requires that the 4th position can be identified, so no assumptions about the missing values are needed. For the mean, the situation is different. It requires all 7 values to be known. If any value is censored, the exact mean cannot be determined. In this case, the 2 observations reported as less than 2 are unknown, so their values must be guessed. You can still compute a mean using substitutions, but the result will be biased. In left censoring, values below a certain threshold are unknown, so the smallest observations are incomplete. Because of that, you evaluate the data starting from the largest values and work downward. The requirement is that there must be enough fully observed large values so that the 4th value, which is the median in a sample of 7, falls within the observed region. In right censoring, values above a certain threshold are unknown, so the largest observations are incomplete. Because of that, you evaluate the data starting from the smallest values and work upward. The requirement is that there must be enough fully observed small values so that the 4th value, which is the median in a sample of 7, falls within the observed region. With censored data, the mean guesses what it can't see, while the median sticks to what it actually knows. Now here's the challenge problem for today. A clinical laboratory measures serum potassium concentration in millimoles per liter. Suppose the laboratory's reporting system only includes results between 3.0 and 6.5. Any patient whose true potassium value falls below 3.0 or above 6.5 does not appear in the recorded data at all. You are given the following observed potassium values: 3.4, 3.7, 4.0, 4.3, 4.8, 5.1, 5.5, and 5.9. Based only on the recorded data, can the mean and median of the underlying patient population be inferred, or are they sensitive to values that may not appear in the sample? Is this problem the same as censoring, or is something different happening here? You may pause the video if you need additional time to consider your answer. From the recorded data, we can compute the mean and median of the observed sample. But these summaries describe only the values that were actually recorded. What's missing are the values outside the recorded range. We don't know how many observations are missing, whether they tend to be low or high, or how they would affect the center of the distribution. Even with complete data, population quantities are only estimated from a sample. Here, with missing values, any estimate would also depend on assumptions about the unobserved data. This is truncation, not censoring. With censoring, the observation is still present, and some information about extreme values is retained, even if the exact value is not known. With truncation, those observations do not appear in the data at all, so information about extreme values is completely unobserved. Because of this, the observed data alone are not sufficient. Any estimate of the center must depend on assumptions about the unobserved values. As the title of this channel suggests, I'm a traveling medical data scientist. Today, I'm sharing footage I captured in North Cotabato in the southern Philippines. It lies far from the usual tourist routes, which helps preserve its pristine character. What makes this place distinctive is that the water does not fall from a river above. Instead, it seeps directly from a vertical rock wall, forming a curtain of thin streams. The entire cliff is covered in bright green moss, giving it an almost deliberately designed appearance. That's all for today's video. If you learned something new about the mean, median, and censored data, leave a comment below. If anything was unclear or unexpected, I'd be interested to hear that as well. Thanks for watching. This is Jose B., the traveling medical data scientist, signing off. See you in the next video.